think we had almost covered entropy. Entropy was disorder, and things liked to gain disorder, and they would move towards disorder. And they would move towards disorder when bonds would break, when intermolecular forces would be overcome, when there's a change of state, when there's a lot of gas molecules being formed. If they're in the same state, then the number of particles increase. So that is when disorder would be created, and you had to figure out the sign of delta S. And I told you what is delta S? Delta S is basically the amount of work that is done at a specific temperature by the substance or by the reaction or by whatever is happening. So that is the change in entropy. It's the amount of work that is either done, or the reverse would be that the atmosphere would be doing work and the piston would be moved downwards. So whenever there are more gas molecules being produced, a lot of disorder is created and the piston moves upwards. So delta S is delta Q. It's the work that is produced. That's why there's a negative sign. It's exothermic at a specific temperature in kelvins. So standard delta S is or was so your standard delta S had a unit of joules per mole per Kelvin. So it's the amount of work. And then we did that to figure out the entropy change. You just have to find out the entropies of the products, which would be given in a table, minus the entropy of the reactants. That would give you the entropy change of a reaction if so if the entropies were known. Now, this is what we were up to. I told you that there's a thing called Gibbs free energy, that whenever you have something happening, whenever there's a reaction, a chemical reaction, work is produced or consumed. So energy is produced in two ways. It's either the heat energy that is evolved, like you burn a match and heat is produced, or it's the disorder that is created, which makes the piston move, which makes your car tires explode. So there's a lot of disorder being created, and that produces a lot of work. So there's energy that is due to entropy change. There's energy that is due to enthalpy change. Gibbs free energy is the total energy. It's the enthalpy change plus the energy that is due to entropy change, and that is minus T times delta S. Because we had earlier stated that the formula of delta S is, we had earlier stated that delta S is minus delta Q over delta T. It's the amount of work that is produced at a specific temperature in kelvins. You rearrange this term, T multiplied by delta S is delta Q. And this is your Gibbs free energy. And what does the Gibbs free energy represent? It represents whether the reaction is going to be feasible or not feasible. So if overall it's coming out to be negative, that kind of indicates that it is exothermic. That means the reaction, the system is producing energy. If it's coming out to be positive, that means the system needs energy, the reaction needs energy, and the reaction is not going to happen until and unless it gets that energy. So we had started talking about predicting whether the reaction is feasible or it's not feasible. TK, we had started talking about this feasibility. So now, I don't know if we did any examples. And just hold on a second. So, but we did started talking about, I think, this reaction. Just a second, my board. So hold on one second. ठीक है बाज़ा, I think I do have that. Just one. Something wrong with the board at the moment. Now this one. And hold on a second. So it's talking about water liquid turning into water gas. Let me just reload everything. Now it's fine. So we talk about water liquid turning into water gas, and we wanted to know whether this reaction is going to be feasible or not at higher or lower temperatures. So it's a boiling reaction. So it's pretty obvious that if you want to boil it, you need a high temperature. So boiling happens at, we know that boiling happens at high temperatures. So that kind of indicates that the reaction is going to be more spontaneous at higher temperatures. Like if I give you three temperatures, 0 degrees centigrade, and there's 50 degrees centigrade and 90 degrees centigrade and 150 and let's say 1000 degrees centigrade. So the reaction is going to be more spontaneous at temperatures that are higher than 100. At a certain point, the reaction becomes really very spontaneous. So it's going to be spontaneous under these conditions. So we're going to try and understand why the spontaneity of the reaction continues to increase as the temperature of the reaction increases. So the enthalpy change of this reaction, it's an endothermic reaction, liquid to gas. That's it requires energy. You would have to break the hydrogen bond, so it requires energy. The disorder increases because gas is produced, so there's higher disorder. So that means delta S and delta H both are positive. So if I use Gibbs free energy and try to justify why this reaction is spontaneous, the reason is we know that delta G is equal to delta H minus T times delta S. And we know that delta H is coming out to be a positive value in this case. It's an endothermic reaction, minus T times delta S, that's also positive. Now, based on the signs, one of the terms is a negative term. And one of the terms is a positive term. The first term is actually positive, and the second term is actually negative. Now, for a feasible reaction, delta G should come out to be negative. If I want this reaction to happen, for feasible reaction, delta G has to be negative. It should be less than 0. And the only way it could be less than 0 is that the negative term is bigger. So that's the only way that's possible, if the negative term comes out to be bigger in size. And to have a bigger negative term, T has to be large. So T should be large over here. So if you make this bigger, the overall delta G would come out to be bigger. So hence the temperature should be as high as possible. So is this clear, this example? Zaib, is this clear, Bar?
Yes, sir.
Achha, so you'll
See, negative term, what does that mean?
listen, it means that reactions produce work in two ways. One is the enthalpy change, and the other one is the work that is produced due to entropy change, right? You clear, bro?
Yes, G.
So the thing is that if the reaction is producing work, whether it's producing work in form of enthalpy change or it's producing work in terms of entropy change, the reaction will most likely be feasible. It doesn't need your help. Okay? Lekin vice versa, if the enthalpy change is endothermic and the energy that is produced by entropy change, that's also endothermic. So overall, the reaction needs energy from outside. It needs your help. So that means the reaction is not going to happen until you give it energy. So the thing so for every reaction, we want delta G to be as negative as possible. We want to make this negative, right? And the only way delta G could be negative is that the relationship between Gibbs free energy and enthalpy change and entropy change is this. So you want delta G to be as negative as possible, and that's only possible in this scenario. Iska delta H is coming out to be positive, and the delta S for this reaction is coming out to be positive as well. If you input positive terms into this, one of the terms
we want delta.
Kya question hai? What's your question?
Okay, delta H should be greater in negative value or delta T, delta S. I mean,
Listen,
or has to be more negative.
We can't change delta S or delta H, right? That's one thing. I mean, if you're burning a match, it's always going to be exothermic, right? So you can't change the signs, but when you input the signs, I mean, this was positive. Delta H, well, what is delta H? It's an endothermic reaction, right? So it's going to be positive, right? Is that clear?
G.
And what is delta S? Delta S is there's a gain of disorder, so that's positive as well. So if delta S is positive as well, so it's a positive value minus T times a positive value, right? So that would make the first one a positive term and the second one would be a negative term, right?
Exactly.
And delta G would be a sum of both terms, right?
Yeah.
Now, if you want to have a feasible reaction, delta G should come out to be negative. I mean, this delta G over here, the overall energy, Gibbs free energy should come out to be negative. That is only possible if the negative term is bigger in size and the positive term is small in size. Is that clear?
G.
So how can you make the negative term bigger? Okay, the temperature at which you're doing this thing have a higher temperature.
Take.
So remember, the only thing, you'll always have two terms. One of the term would be fixed, but the other term could be, you can make it bigger, you can make it smaller, because it's being multiplied by temperature. So you can either increase the temperature or you can decrease the temperature. So let's do another one, a very similar one. Okay, I want to figure out, I have this reaction going on and it's freezing, right? And I'm freezing water. And I want to know, when will this reaction be feasible? Like qualitatively speaking, should it be lower temperature or higher temperature? When would this be feasible? Should I decrease temperature or should I increase temperature?
For doing what? For making it feasible?
Water liquid to water solid. freezing.
जी,
तो क्या होगा? Temperature should be kept low or high?
low I
See, in this case, you got to have the temperature as low as possible. Only then will this reaction be feasible, right?
जी,
I said, now we know this obviously because it's freezing. We know that freezing happens at lower temperatures. It doesn't happen at higher temperatures. Now, the same thing we're going to derive using Gibbs free energy, that I know that this reaction has a negative enthalpy change. It's exothermic, right? Molecules lose energy to gain to turn into ice. And I also know that the entropy change delta S for this reaction is also liquid to solid. So that's a decrease in disorder. That's also negative. Is that clear? Both of them are negative. So that means
yeah,
delta G is equal to delta H minus T delta S, right? Now delta H has a negative value. That's fine. And minus T times delta S also has a negative value. So that means one of the term is actually negative, this first one. The second term, because of two negative signs, would actually be a positive value, right? So if I want to make delta G negative, because I don't want delta G to be positive, that would indicate that the system needs energy from outside. So if I want to make it negative, if I want to make it feasible, what should I do? Higher temperature or lower temperature?
lower temperature.
Okay, because if I use a lower temperature, then this term becomes smaller in size. And so I want to make this, I want to keep this as small as possible. And to keep it as small as possible, what I'll do is I'll have a lower temperature. I'll use a lower temperature for this reaction. So is this clear?
Yes, sir.
Now we can apply this to pretty much any reaction. The same thing. Like if I have the Gibbs process and I want to know when will this reaction be more feasible? I mean, the Gibbs process is N2 plus 3H2. And I want to know when will ammonia be formed? Would it happen? Would ammonia be formed at a higher temperature or lower temperature? So the first thing is the enthalpy change for this reaction is already given. It's negative. It's minus 88 to be more precise. And the entropy change is negative or positive? What is the entropy change?
Yeah, it's negative. Yeah, negative.
The number of gas molecules are decreasing. You had 4 molecules of gas, and now on the other side you just have 2 molecules of gas. So the molecules of gas are decreasing. Both of them are again negative. So that means delta G is equal to delta H minus T delta S. So T delta S, and if I want, the first term is negative, the second term is also negative. So a negative T multiplied by something that's already negative, that's actually positive. So the first term is actually negative, and the second term is actually positive. And again, to make delta G overall come out to be negative, that's the only possibility is that you get rid of the positive term. You have a smaller T, or you use a lower temperature. That's what you're going to do. Okay, right? Is that clear? So the Haber process will happen at a lower temperature. Clear? Is this clear?
Yes, sir.
And you can make a table of different and you can, so certain reactions would happen at higher temperatures, certain reactions would happen at a lower temperature. So let's talk about the combustion reaction that's taking place in your gas heaters. You've got methane. It's a gas, it burns I said not methane. Let's talk about octane, petrol burning. So I've got octane. I react it with oxygen. And CO2 and H2O are going to be produced. So there's 8 CO2 and 9 H2Os that are produced. And let's say they're all produced in gaseous state. Petrol was a liquid that burned. And you can balance it. It's 8 CO2 and 9 H2O. So that's 25, 12.5 O2. So clearly delta S over here is positive. And delta H over here, it's the enthalpy change. It produces heat, so that is also negative. So when will this reaction, like burning petrol, when will this be feasible? I'm going to use Gibbs free energy. Higher temperature or lower temperature? What temperature should I?
No, with high temperature. High temperature.
So let's say delta H minus T delta S. So delta H is negative.
Low temperature.
Minus T multiplied by delta S is positive, right? So that means the first term is negative and the second term is also negative. So both terms are coming out to be negative. So that means it's always feasible. I mean, you can burn petrol at any temperatures, but you can't freeze at any temperature. It has to be a low temperature. So this one is always feasible. It's going to get more feasible if the temperature is increased. So you're going to become more feasible as temperature rises. TK, is this clear?
Yes, sir.
Yes, sir.
Achha, so one thing is the qualitative assessment of when will reactions be spontaneous, and the other one is you're going to put values, use values. So I'm just going to quickly move to directly to questions. We'll have the same. क्या question है?
जी क्वेश्चन ये कि I mean फिर तो at room temperature even I mean ये feasible reaction होता even at room temperature.
Which one?
I mean the reaction of petrol burning petrol.
No, that was feasible at any temperature. Okay, it's always coming out to be negative.
So but petrol doesn't burn at room temperature or does it?
It burns at room temperature perfectly well. But petrol is very flammable.
I mean exposing petrol to air will make it burn.
It burns very quickly. So so it is feasible. Now about this delta G, we'll do just past paper questions. One second. And now we're going to do specific delta G questions with values in them. So over here, he's saying calculate the temperature above which the reaction one is not spontaneous. I mean, I'm directly jumping to this question. So the reaction number one is not spontaneous. I mean, the reaction number one is given. So for it to be non-spontaneous, delta G has to be positive, right? So what is delta G? Delta G is equal to delta H minus T delta S. So it's supposed to have a positive value. That means this must be greater than, it's got to be greater than 0, right? So that means delta H minus T delta S must be greater than 0 for the reaction to be spontaneous. And he's asking us the temperature above which. So I'm just going to plug in the values. The delta H values are given over here somewhere. Neither given over here. It's minus 640 kilojoules. So it's given as minus 640 kilojoules per mole. That's provided. Minus temperature, I don't know. Delta S value is also provided over here. It's minus 225.7 joules per Kelvin per mole. So it's minus 225.7. And it's joules per mole per Kelvin. And this value must be greater than 0. So I've just plugged in the values. The only thing that you have to be always careful about is that enthalpy changes are in kilojoules, while entropy changes are in joules. So this thing needs to be divided by 1000. So it's minus 640. You take everything else on the other side of the inequality, it's going to be T and minus 225.7 divided by 1000. Remember, when the minus sign changes, when the sign changes, the inequality flips. So if I make both signs plus, the inequality that's in between, that's going to change. So it would be facing this side now. Take this to the other side and it's going to be into 1000.
So have you considered ये delta G आपने 0 consider किया?
वो तो नहीं है. नहीं, he's saying कि calculate the temperature above which the reaction is not spontaneous. So when is the reaction not spontaneous? When delta G is positive, right?
G. Yeah.
So,
Achha, so it has to be.
So that's the inequality that I have, and I just solve. I plug in the delta H values, I plug in the delta S values. The thing you have to be careful about is this thing. You have to make sure that entropy change values are in joules, while enthalpy change values are given in kilojoules. So make sure you're using the same unit. So I've converted entropy into kilojoules by dividing 1000. That's going to be my answer. If I multiply that, it's going to be 1000. Like if I do that. So what do I get? That's 1000 multiplied by 640 and divided by 225.7. So the temperature I'm getting above which it's 28.4 kelvins. Is that clear?
Yes, sir.
Yes, sir, in this equation, the T is negative and delta is also negative. Won't the whole thing be positive?
I think what did I do? I took it to the other side first. So the T became positive, right?
Yeah.
Okay. What you can do, you're right, you can do this, but so if I take it to the other side, then this entire thing would become negative, right? Clear? So this would be
Yes,
negative,
sir.
and this would be negative. Both sides would be negative, and then we'll try and do another one. All you have to do is you've got to plug in the value. So so like over here, He's saying that now over here he's saying the amide bonds can also be formed by the reaction of whatever there's a reaction happening and the enthalpy change is given. Calculate the minimum entropy change for this reaction to be spontaneous. So it's the same one. It's you got delta G is equal to delta H minus T delta S. So for the reaction to be spontaneous, this entire thing should be less than 0, right? So you start plugging in the values. Delta H is already given, it's minus 6 kilojoules per mole. And minus T multiplied by delta S. I don't know what delta S is, so I'm going to put X over here. This must come out to be less than 0. Now, if I solve this, it's minus 6 on one side. The temperature is given, that's 298 Kelvin. So if I go take that to the other side, that's 298 into 298x. And the inequality sign is not going to change. It's just going to go to the other side. Okay, so remember, unless you're changing the sign, whenever you're changing the sign, the inequality changes. So you've got this, and this is in kilojoules because you took enthalpy change in kilojoules. So your delta S, which was X, came out to be greater than or equal to minus 6 divided by 298. And it's kilojoules per mole per Kelvin. Is this clear?
So do we have delta S? Do we have delta G Gibbs value, Gibbs free energy? अच्छा वो
नहीं,
ऊपर
वो
से calculate.
उससे कहा हुआ था कि you just had to make it spontaneous. So that means you just want it to be less than 0, right?
Yeah.
So that means delta H minus T delta S should be less than 0, right? So I just ended up solving this.
Oh yeah. ठीक.
So here's another one. He's asking you to calculate delta G at 225. So delta G is equal to delta H, which is given over here, is minus 602. Minus T, temperature is given 25, but should be in Kelvins. So T delta S. And I have no idea what delta S is, but I can calculate delta S separately. Delta S, we studied earlier, is the entropy of the products if it's given, minus the entropy of the reactants. So it's the entropy of the products minus the entropy of the reactants. And what do we get? We get the product is 26.9 minus the reactant. The reactant is Mg, which is 32.7 and half of O2. So that's going to be 205 divided by 2. So product minus reactants. I'm going to plug in this value into this equation and I'll get delta G. Okay, all clear?
Yes.
So just remember, it's going to be your products minus your reactants. That's entropy change. Gibbs free energy is enthalpy change minus T times delta S. So it's the energy that is due to entropy change and add the energy that is due to enthalpy change. If both of them come out to be, if overall it comes out to be negative, that means it's a spontaneous reaction. It just produces work, doesn't need work. If this comes out to be positive, that means it's not a spontaneous reaction. So let's continue tomorrow. Okay.
ठीक है sir.
Okay then.
चलो okay sir.
Thank you, sir. Allah Hafiz.